Yeah, welcome to this bonus session. That's the one on Boostgraph for beginners, or it should have actually been Boostgraph for beginners from a beginner. So I'm not an expert on Boostgraph really, but what I'm trying to do in this talk, I'm trying to give you an idea how to start using that library. Why am I standing here if I'm not an expert on this library? I was here at this conference last year and I was talking with some guys about the Boost libraries, and these guys also working for a big famous company in IT, so probably very smart guys. They said they were looking at the documentation of Boostgraph and they had really trouble trying to find out how to use this library. And if you check the documentation yourself, it's huge. You can read and read and read and you never seem to finish. It takes even more time to play around with all the different classes and functions in that library. And if that is not enough, there's even a book written by the authors of the library. I think it has 350 pages, and it's just about one Boost library. So you can spend a lot of time just learning about Boostgraph. What I did when I talked with the guys last year, I sat down and I tried to come up with a presentation which gives people an idea how to start using that library without going through that documentation and finding out certain patterns yourself. So that's the idea about this library. Unfortunately, as I noticed, the guys I talked to last year, they are not here at this conference. So I presented now something, or I'm going to present something they are not going to benefit from. So yeah, if you like, we can actually cancel the whole thing and enjoy lunch. But yeah, as I prepared now something, I'm just going ahead now. Feel free to interrupt me at any time. I'm trying to do my best to answer the questions. I hope we can also finish, I think, in 75 minutes. I think that's the time frame we have. Then there's a little break again. Maybe we can grab another pizza, and then it's getting into the next session. So this talk is about Boostgraph, and I believe most of you have probably an idea what Boostgraph is about. Otherwise, I wouldn't know what you're doing here in this room now. When I hear graph, I always think of a subway map with a couple of stations and a couple of lines. And I imagine I'm at one station, I need to get to another station, and I try to find the shortest path from one station to the other. That's one of the problems you can solve with a library like Boostgraph. That also means that when you use that library, there are really two steps involved. First, you have to describe the graph somehow in C++. And in the second step, you will use one of the many algorithms the library provides to, for example, search a shortest path in the graph. That's exactly what we're going to do now, though we have two parts here. In the first part, I'm going to talk about how to define a graph with that library. That's typically something everybody will understand. That's really simple. And the second part is about how the heck do I use the algorithms from Boostgraph, because that's where I believe most people have problems with, and we are going to spend more time on the second part then. All right, again, if you have any questions, feel free to interrupt me anytime. That's a quick overview what Boostgraph has to offer. So we find in Boostgraph a couple of classes to define graphs, but much more importantly, we find many algorithms, for example, to search for a shortest path in a graph. I'm not going to talk much about the classes we find in that library. There's one class I'm going to use in all the code examples you're going to see. That is this one here, adjacency list. And this is a talk for beginners. I'm not going to talk about the alternatives. For now, we're just using this one class, adjacency list, to define our graphs. If you happen to define graphs yourself already with some other types, you will also find in this library adapters. So if you have used already a vector, for example, and you have a graph definition already in your code, you don't want to change your code, use another class here from Boostgraph, you might find an adapter in that library which you can just use to wrap your existing graph definition. Then, more important are the algorithms, and there are two core search algorithms. They are called breadth first search and depth first search. I'm not sure whether I have to explain much what these algorithms do. To give you a brief idea, the breadth first search algorithm starts at a certain vertex, at a certain point in a graph, and visits then all the vertices next to it. Then it gets to the next outer ring and visited those next to it. So it's a little bit like throwing a stone into the water, and you have a wave going then in all directions. The depth first search does the opposite. It goes to the next vertex, and then to the next one, and to the next one. It goes as far away as possible. So it's a bit like a star, and it's just two different ways of visiting all vertices in a graph. As you see here, we have to pass a couple of parameters. It doesn't matter at this point what these parameters are. I wrote these algorithms, or I wrote these two signatures down more because of this return type void. So if you think of algorithms, and you think especially of the algorithms in the C++ standard library, you would maybe expect that if you call these functions here, that they give you something back. For example, you call an algorithm, you want to find the shortest path between two vertices, so you would expect that there's a return type. But if you use these algorithms, there is no return value. So how do the algorithms work? They work with visitors. So what you have to do if you use these two algorithms from Boost Graph, you pass a visitor here. And what these algorithms do, they just walk from one vertex to another. And whenever they find something interesting, they tell your visitor, by the way, there's a new vertex. Or, by the way, there's a new edge, a new line between the vertices. So it all comes down to the visitors, what you're going to do with these two algorithms. Apart from these two core search algorithms, there are a couple of other algorithms implemented based on these. So there are algorithms which have, for example, shortest path in their name. So if you don't want to call an algorithm and just go from one vertex to another, but you want to do something more concrete, you will find algorithms like Dijkstra shortest path in that library. If you look then into that algorithm, how it's implemented, you will see it's implemented based on, I believe, breadth first search. So you can use these algorithms yourself, but there are also more specialized algorithms if you know what you want to do. Oh, sorry. Pardon? If? The question is whether I can define vertices and edges. Okay. So if you think of a subway map, and you have the stations in a subway map, the stations are the vertices, and the lines between the stations. If you want to go from one vertex to another, these are the edges. So I have to come up with a simple graph for this talk, and I don't want to use the subway map of Tokyo or New York because it's difficult to talk about it then. So I've been coming up with the simplest graph possible, which is still a little bit more interesting than having just two vertices. So this is my graph, which I'm going to use for all the code examples you're going to see. So I have 4 vertices, and I'm calling them top left, top right, bottom left. And I can go from the top left vertex to the top right vertex. I can also go to the bottom left vertex, but I cannot go to the bottom right vertex. So I have 4 vertices. I have 4 edges, and I can go in both directions. So I can go here from top left to the bottom left, or I can also go from the bottom left to the top left. So everybody has now to remember this thing, because I'm going now to the next slide, and that's the graph I'm going to talk about all the time. All the code examples you're going to see will assume that this is a graph we're going to work with. All right, first part of the code examples we're going to see is about how do I define this graph now in C++. I'm going to use my adjacency list class, the only one we know at this point. And you see we have to add here the appropriate header file. There is not one header file which includes everything. We have always to pick the header file depending on what we need. So there's one called Boost Graph Adjacency List, HPP. You also see that everything which is defined in Boost Graph is in the namespace Boost. So there's nothing like Boost Graph or something else. It's just Boost. And you see adjacency list is a template, but at this point we don't care about the template parameters either. We just instantiate adjacency list and have our graph. By default, a graph doesn't have any vertices, doesn't have any edges. So we need now to add the 4 vertices of our graph, which we have just seen on the previous slide, to this object. And we do this by calling a function addVertex 4 times. The first thing you will see when you use that library, that nearly all functions are implemented as global functions. So I think there's just one member function here this object has. I believe it's clear. But apart from that, all the other functions you're normally interested in are global functions. So in this case, you call addVertex, you pass the graph as a parameter, and 1 vertex is added to the graph. As my graph consists of 4 vertices, I call the function 4 times. And you see I also get a return value here. It's a so-called vertex descriptor. So I have here something in case I want to refer to the vertex somehow which was just added. Yeah, the question is whether it's truly global or in the namespace boost. It's in the namespace boost, yes. Yeah. What I meant was add vertex is not a member function. You cannot call g.addVertex. Yeah. Pardon? The reason is I think they're trying to make the library as generic as possible. And they say everything has to be then, yeah, a global function. But apart for us, it's not really different. So, yeah, there would be no difference calling g.addVertex or doing it like this. All right, at this point, I've added 4 vertices to the graph, but they're not yet connected. I didn't define yet any edges. I just have, yeah, it's like a subway map with 4 stations, but there's no way to come from one station to the other. Before I add now some edges, let's play a little bit around with these vertices. Once I have added vertices to a graph and I want to get them somehow, let's say I didn't store the return value somewhere. I still want to get the vertices somehow. I can call another global function in the namespace boost called vertices. Vertices returns a pair of iterators, begin and end. And I can use this pair of iterators now to iterate over all the vertices in the graph. And here I'm just printing the vertex descriptor to the screen. So what do I get? If I run this code, I will see 0, 1, 2, 3. Why that? Internally in the graph, there's a vector used. Every time I call addVertex, a vertex, an element, is added to the vector. The first vertex is at the first element in the vector, and thus has the index 0. So these are simply indexes into the vector in my graph object where the vertices are stored. I can also check here the type. If I print something like this here, 2 standard cout, I get standard size t, or actually unsigned int64. So this is just an index into a vector inside the graph. All right, at this point we have 4 vertices. Now we want to connect these vertices somehow. And I'm doing this with a function called addEdge. We have not only addVertex, but also addEdge. Again, it's a global function, so there's no member function called on G. I have to pass my graph G as a parameter. And as I have to create edges by connecting vertices, I pass here every time 2 vertices as parameters to addEdge. So if you remember, I have this graph with the 4 fields. I want to get from the top left corner to the top right corner. This is here, vertex 1 and vertex 2, then vertex 2, vertex 3, and so on. So I create the edges between my 4 vertices. Again, at some point, I might want to access all the edges in a graph. There's another helper function called edges. It gives me, again, a pair of iterators. Again, I can iterate over all the edges, and I can print them to standard cout just to see what I get. And I get then something like this. So each edge is defined as a pair of vertices. Yeah, I think it's very intuitive. Timo? Yes, good question. Timo was asking what the bool thing here does. So addEdge returns not just an edge descriptor, but actually a pair of an edge descriptor and of a bool. And I can check here the bool variable, whether the edge could be successfully added to the graph. And depending on your graph, if you have directed and undirected edges, depending on these kind of things, it might be that you're trying to you might be trying to add an edge which the graph can't take anymore. So in this case, I didn't check because here it's no problem. Yeah, okay, this is maybe going now into your direction. In this case, I define my adjacency list by passing some template parameters. And I have been telling you before that internally in the graph, there's a vector used to store the indexes, to store the vertices. And I can actually specify when I instantiate the adjacency list what kind of container should be used internally. What you see here are the default parameter values. So by default, a vector is used internally to store the vertices. this thing means a vector should be used. That S stands for selector. So it's a type provided by Boostgraph. This is a vector selector. This thing here means what container should be used internally in graph to store the edges. As we see again, there's a vector used internally. Every time I call add edge, the edge is stored internally in a vector. And this here means whether the edges should be directed or undirected. So whether I can go from one vertex to the other or also on the same edge the other way around. The default is directed. In this case, for my graph, I want to go from one vertex to the other, no matter which direction. So I have to pass here the undirected as the undirected selector. So I basically start new again. So what you have seen on the previous two slides, forget about it. I create my new graph. I have now here defined the undirected S. I want again to add my 4 vertices and my 4 edges. But what you see here now, we don't need to explicitly add vertices first. We can just call 4 times add edge. And then we pass in here the indexes of the vertices, which are going to be used here in the vector. And the graph realizes, oh yeah, here you are using an index 1 and an index 2, something like this. The graph sees, oh yeah, these vertices haven't been added yet to the vector, but add edge does this automatically. So all I need to create my graph, as we have seen it a couple of slides ago, all I need to do is I need to call add edge 4 times. In this case, I even use some more descriptive names, not some integers. And after that code, I have my graph defined. There are other ways to define graphs. It's also possible to pass the edges somehow directly to the constructor. But at this point, we have seen how we can define our graph. And I definitely want to concentrate more on algorithms. So I believe that's what more people have problems with. All right. We have now our graph defined. Now we just want to do something with it. We want, for example, to visit these vertices in the graph. We want to use a visitor. We want to find a shortest path between 2 vertices, something like this. Before we look at the code and see how we can actually call algorithms, we have to make a couple of decisions. First, we have to think about whether we take one of these core search algorithms, like breadth first search or depth first search, or whether we take a more specialized algorithm, like Dijkstra, shortest path, or one of the other, I don't know, dozens algorithms defined by the library. That's normally the first thing we have to think about. But that's, I think, just natural. At some point, you know what you want to do with your algorithm. So you look at the documentation. You see different categories of algorithm. Depending on what you need to do, you pick the algorithm you need. What's getting a bit more complicated, and I think that's where people start to have the first problems with, there are 2 versions of every algorithm. The one version has named parameters. The other version has non-named parameters. So what does this mean now? If you call, for example, the algorithm breadth first search, you will see in the documentation that you must pass 5 values. There are 5 parameters expected. That's the non-named version. That's what you normally do when you call a C++ function. There is a certain signature. A function expects 5 parameters, so you have just to pass 5 values to it. But there are often situations where we don't care about a couple of these parameters, where we really want to pass only 1 or 2 parameters to the function. In this case, we can use the named version of the algorithm. At this point, we are not yet done. We will see that there are also algorithms which expect certain properties. For example, when we think about how breadth first search works, that is an algorithm which goes from one vertex to the other. The algorithm needs to remember somehow whether it visited a certain vertex already before. It will just go along the edges, and there's a new vertex, and oops, there's a vertex which I've seen already before. So somewhere the algorithm needs to store the information whether a vertex has already been visited. And the algorithms here in Boostgraph, they use for this so-called property maps. So what you can think about is that there is a property attached to a vertex or attached to an edge, and that property is used to store some extra information for a certain vertex or for a certain edge. So when it comes down to breadth steps first, the property map which is used here, if you know a little bit about graphs, is a color map. So we are using a color to mark a vertex, whether it has been visited already before or not. And this color needs to be stored somewhere. And breadth first search, this is really difficult to repeat all the time. Breadth steps first uses a color map to do this. Why do we need to care about it? I mean, if you use algorithm from the C++ standard library, that is an implementation detail. I mean, if an algorithm needs a color map, why does it not just simply create a local variable and uses its own color map? In fact, we have algorithms which work like this. So especially if you use here a named version of an algorithm, you just pass the object you're interested in. So for the other objects, the algorithm will just create variables on the stack. So we don't need to care about them. But unfortunately, there are sometimes algorithms where we need to take care of the properties. When we think, for example, about an algorithm which should find the shortest path between vertices, and the edges have weights, so it's more expensive to go over a certain edge than over another, then we need to assign somehow a weight to an edge. And that means we need to use one of these property maps, so we need to understand how this works. Otherwise, we will not be able to use the algorithm correctly. So all of this comes together when you look at the documentation, and then people are like, oh, maybe I can use another library. But we are going now step by step through some source code examples to see that all of this is hopefully not that difficult as it sounds. Very first example. I'm using my breadth first search algorithm, and I'm using the version with the non-named parameters, which means I need to pass as many values as this algorithm expects. If you look up the documentation, you will find this algorithm, and it says you need to pass 5 parameters to it. All right, so that is what the algorithm wants, so I'm going to do this. First parameter is my graph. The second parameter is the vertex where this algorithm should start to visit other vertices from. The third parameter is a queue. It's already a bit strange, but yeah, if we use the non-named version of this algorithm, we have to pass it. The algorithm expects us to pass a queue here. All right, so I pass a queue. The fourth parameter is a visitor. In this case, I use a visitor from the library, a null visitor, so nothing's going to happen when I run this code. But all right, we can understand that this could be interesting for us because it will tell us when a new vertex is, for example, found. And the fifth parameter is the column map I was just talking about. It provides this algorithm a container where the algorithm can remember whether it visited a vertex before or not. If you compile this code, it all works, but you don't get any interesting result, as obviously the visitor, it doesn't get notified if the algorithm finds anything. But what you also see when you look at this algorithm, you're also looking at this queue. You may be also looking at this color map, and you are like, why should I need to pass a queue and a color map to this algorithm? Can't the algorithm just create its own queue and its own color map? And in fact, it can. Oh, sorry. I was afraid that you were asking this. I have no idea what this queue is for, so the question is what the queue is used for. If anybody knows, I didn't check the implementation. I can easily understand and explain what the color map is used for, but I didn't check the queue now. Yeah. So especially in a situation where you even don't know why you pass certain objects to the algorithm, it's, I guess, a good idea to switch to the other algorithm where you only pass parameters by name. So you don't need to worry and don't need to care about this other stuff where you even don't know why you are passing it. So in this case, I want to use my breadth first search algorithm again. The only thing I'm interested in is really the visitor. This algorithm should create its own queue and its own column map on the stack. And in fact, it does. Good, that's perfect. So I use now only my visitor. And as I use now the named parameter version of this algorithm, I need to make it clear to the breadth first search algorithm that this one here, this thing here, is a visitor, another queue, another column map. So I need to give this parameter a name. And I do this by wrapping this object here with this visitor function, a function also provided, obviously, by BoostGraph. So I can now give parameters a name by wrapping them with a function provided by the library. You see, I don't pass the queue anymore. I don't pass the color map anymore. It's only the visitor passed. And breadth first search understands that this thingy is a visitor because I named it. Yes? Yeah. Yes, I can also imagine that it is a kind of a optimization mechanism, because if you call this algorithm a couple of times, you just create the object once and then you just pass it. Instead of recursion, you're using it here as a stack of the vertices with the okay, hopefully this was loud enough for the camera. Yes, next question. What do you mean by if you just pass this thing, this object, breadth first search doesn't know what this thing is. So it could also be something else. It could be also, for example, the color map. So you need to give this thing a name, and you do this by calling a function from that library. And then breadth first search understands, this is not a color map, which we understand by looking at the rest of the code. But by wrapping this thing with the visitor function call, breadth first search understands, okay, this is a parameter, it is passed by name, and the name of this thing is visitor. Yes, indeed. Yeah, there are really two versions of the functions only. That is the one, the non-named version. You have to pass as many parameters as the algorithm expects. That is the other one, where you are flexible. You can pass different parameters, but the algorithm needs to find out what is the parameter you pass now. You have to give it a name. It's not really a name here. It's not a string, but it's just a way to mark this object somehow. And for that, the library provides these helper functions to wrap the object and to make it clear. This thing which I pass here is not a color map, it's a visitor. Pardon? I didn't understand. Why can't it identify it by the original type? I think the more we go through the slides, the more questions are there, like why does it work like this and why doesn't it do this? And I have a couple of more examples where I also wonder, why is this the code I have to write? Yeah. Okay, now I want to change this example a little bit. So far I've been using a null visitor from the library. I want now to create my own null visitor just to get an idea how this works. How does the code look like? At this point my null visitor doesn't do anything either, but at least I get an idea how I define my own visitor. So let's maybe start here from the breadth first search invocation again. All right, I have again the named version of the algorithm. I don't pass all the 5 parameters, but only the ones I'm interested in. I'm passing here the visitor. This time the visitor is based on my own class, my null visitor. We see the null visitor is defined here. It's a simple struct. The most important part is maybe here the operator. That is the function which is called whenever the algorithm finds something interesting. We see that there are 2 parameters. The first one is either a vertex or an edge. The second one is always a graph. So in this case, it would always be G. And we need to tell the visitor somehow when it should actually be notified. And we do this with this type def here. There's an event filter thingy defined. And Boostgraph provides various tags which we can use here to make sure that our visitor is notified when, for example, a new vertex is found, or when, for example, a new edge is found. In this case, I set the event filter to on no event, which means this function will never be called, a typical null visitor. So again, all of this compiles, all of this works, but in the end, nothing really happens. I don't get any data I could really work with. All right, let's change the visitor to something more useful. I want now to be notified when this algorithm detects a new vertex. So I don't call my class my null visitor anymore. I just call it my discover visitor. And I have to change now the event filter. I'm using now a tag which is called on discover vertex. Yes? That is correct. The question was, what does new vertex really mean? And it means that a vertex is found in the graph which hasn't been visited before. Yes. So I set event filter to the tag on discover vertex. Now I have configured my visitor somehow. And whenever this operator is not called, this T here is a vertex. And what I do, we have seen it before. I can, for example, just write the vertex to standard cout. And we know that the vertex is just a number, 0, 1, 2, 3. And indeed, if I run this code example, I will see something like this, 0, 1, 3, 2. Because the algorithm just goes somehow through the vertices. 0 was the top left, 1 the top right, 3 the bottom right, 2 the bottom left. There's something else which is maybe interesting. You have seen on the previous slide that I wrapped my null visitor here with that BFS visitor class. I don't need to do this. There's a helper function provided. So if I want to use this visitor here with the breadth first search function, I can just call a function like make BFS visitor. Why is this function required? These visitors here are algorithm independent. You can use this visitor also for another algorithm. If I'm not completely mistaken, yes, here's the example. I'm using now my discover visitor, the very same struct, with the depth first search algorithm. It's again an algorithm which just goes through one vertex to the other. And I still want to be notified when a new vertex is discovered. And in order to use this visitor now for this algorithm, I need to call the make DFS visitor function. So I take my algorithm independent visitor, make it algorithm dependent, and then I can pass the visitor to that function. Again, if I run this code, I see now 0, 1, 2, 3, because that visitor does the depth first, and the 2 is the vertex which is furthest away from the 0. I mean, it's the opposite one. All right. When I use that library, I do not need to define visitors all the time. Fortunately, there are a couple of visitors provided out of the box. There's, for example, one visitor which records distances, the number of vertices I have to go to get to a certain vertex. So there's a function which I can just call, which is called record distances. Again, this one returns an algorithm independent visitor. So I have to make that algorithm independent visitor a breadth first search visitor. So I call again my make BFS visitor function. I'm using again the version of the algorithm with the named parameters. So I wrap the whole thing with that visitor function. Let's have a quick look at record distances. How does this thing work? Record distances needs to put the distances found somewhere. So what I do here, I pass an array to record distances. It is important that this array has also 4 elements, because my graph has 4 elements. What I also need to do, I need to configure again that visitor somehow. You remember that event filter thingy. The event filter thingy is set on exactly this type, on tree edge in this case. Why on tree edge? Because the documentation says so. So when you look up the record distances visitor, it clearly says in the documentation what you should set here, that this visitor actually works correctly. And again, what I get in the end is just a couple of values, so I can iterate here over my array when I run this code and print them to the screen. What else I can do? There's, for example, a record predecessor visitor that gets already that gets already interesting, because the record predecessors visitor can help me to find a path through the graph. So how does this thing work? You see it's more or less always the same code now. Breadth first search visitor, make BFS visitor. Then I call the record predecessor visitor here. I again have to pass a container so that the predecessors can be stored somewhere. And again, I have to pass in here a tag so that this event filter can be configured accordingly. Now what I'm doing here, I want to find all the predecessors for each and every vertex, beginning in the bottom right. And all these predecessors are written then to that array again here, which again must have 4 elements because I have 4 vertices in my graph. And I can then, once this algorithm has done its job, I can then look here into my predecessors array, and I can find out how I can get, for example, from the top left vertex to the bottom right vertex. If I run this code, if I print this to the screen, I get here 0, that is the top left. I get 1, top right, and I get 2, bottom right. 1 pass from top left to the bottom right. Okay, let's say I want to record distances and I want to record predecessors. That's again one of the slides where you look at and you wonder why you have to do it this way. Because you can't just pass now 2 visitors as 2 parameters to the function. You see how it works. You have to make a pair of visitors. Here's record distances used again. Here's record predecessors used again. This thing becomes a pair, and this pair becomes a BFS visitor. And if you pass the 2 visitors like this to the function, it works as you would expect it. So you get now the distances and you get the predecessors. What do you have to do when you have to pass a 3rd visitor? You have to nest the pairs. So it becomes a bit ugly. Yes? Pardon? As far as I know, tuple doesn't work. Yes. As far as I know, the question is whether tuple works, and I have not seen anything in the documentation that tuple works. Yeah. Yeah. Was there another question? Or yes.
Why don't you use addresses for storing distances and predecessors? You store static array for storing distances.
Yes.
Why don't you use back insert?
Okay. The question is why I use here an array and not something else like a back inserter to record the distances and the predecessor. What time is it? Okay. If you look at the code, I'm not even passing the array itself. I'm passing a pointer to the array. Boost Graph uses another library here, which is called Boost Property Map. And if I want to use a property map, I cannot use anything else like a back inserter. So a property map is in the end, like a vector again. So on the one hand, I have my vector for the vertices, and somewhere else I have my vector, for example, for the distances. And what now Boost Graph does, it knows that the vertex in the top left corner of my graph has the index 0. So it's the first element in that vector. That is the vector with the vertices inside the graph. And then it looks at the other thing, which is also an array, and says, okay, the distance for the first vertex has the index 0, so I also have to write the distance here at the first element in the other vector. So I'm using the array here because by passing a pointer to the beginning of an array, Boost Graph understands, all right, this is a property map. There are other possibilities to use a property map. So there are other classes provided, but this is more like a trick. By passing a pointer, Boost Graph understands, okay, that's the beginning of the other array. That's where I have to put in the distance for the first vertex. If I want to record the distance for the second vertex, I just increment the pointer. Trying to answer the question in that short amount of time. All right. Now we have been talking already a bit these property maps, and we can also define our properties ourselves. At this point, I'm not using one of these core search algorithms anymore. I'm using the algorithm Dijkstra shortest path. So that's one of these specific algorithms, which is based on one of these core algorithms. And if you know something about it, or actually if you don't know anything about it, Dijkstra shortest path makes sense if you're trying to find the shortest path in a graph where the edges have weights. So there are certain edges which are more expensive to travel on. Which means if we want to use the algorithm, we need somehow to define edges. We need somehow to define weights. We need to attach a weight to the edges. And Dijkstra shortest path needs to be able to find the weight of each and every edge. So how does this work now? Here in this case, I use a so-called property list. The property list has only one element, but I will tell you afterwards how it looks like when you use multiple properties. And it looks a little bit like using multiple visitors where you have to use the pairs somehow in a nested way. But this is an easy example. There's just one property. So if I want to use now a graph with Dijkstra shortest path, I have to make sure that each and every edge has a weight. So I need to tell the graph, make sure that there is somewhere a variable where I can assign a weight to an edge. You see how this works? I have now here my graph class, again based on the adjacency list. I pass in here a couple of template parameters like my vector selector, undirected selector. That is all something we've seen before. And then there are two more template parameters where I can define whether vertices or edges should have properties. Now for the Dijkstra shortest path algorithm, it is important that edges have a property weight. That template parameter here means that my vertices don't have any properties. About the vertices, I don't care at this point. It is also the default template parameter the graph uses normally. But here, I don't use now no property. I use something called property edge weight t int. And that means here, this part means that all my edges have now an edge weight property, and its type is int. This is something which is defined by BoostGraph, so it's another tag I can just use. And if I use this tag here, I have an advantage because Dijkstra shortest path will automatically try to find the appropriate property in the graph. It is namely using this tag. So if I define the graph like this and I say all my vertices should have an edge weight, then I can just call Dijkstra shortest path because the algorithm tries to find the edge using this tag internally. So I don't need to tell the graph somehow, oh, by the way, you need to take this variable to find the weight. This all works out of the box. If you run this code, it works, but there's still something missing. At this point, I have to find a weight for the edges. I mean, there is now a variable somewhere, but I didn't set it yet. So I still need to somehow set the weight. And you see an example here how this works. So here I have the same graph class again with my edge weight property. Here I have the instantiation of my graph, again with the edges begin and the edges end iterators. And I can now pass in here another variable, namely an array, where I have defined the weights. So what this means is that the first edge in my graph has a weight of 2. The first edge was the one between the top left and the top right vertex. So this one here, to cross this edge, is now twice as expensive as crossing all the other edges in my graph. And if I want now to find the shortest path from the top left to the top right, I want the algorithm to tell me you have to go through the bottom left through the bottom left vertex, and not like before through the through the top right vertex. And indeed, if you run this code, it just works like this. I mean, Dijkstra shortest path looks at the weights. The weights are now set internally because you pass this array here to the constructor. The weights are stored internally in this edge weight property, a variable, that's at least what I imagine, a variable attached to each and every edge. And Dijkstra shortest path will automatically find the weight there. There's also a different way to access these weight variables. Instead of passing in here the weights into the constructor, I can get access to that variable by accessing the edges directly. So this looks a bit frightening, but there's more code like this in BoostGraph. What I do here first is I need to access the property map, the container in the graph where the edge weights are stored. And I do this like that. I just wrote down the type for you to see what it looks like. In real code, I would just use auto. So there's a get function, and the get function will get the graph, and will get that tag again, this edge weight t thingy. And get returns a container. I imagine it's simply a vector with as many elements as we have edges. And for each edge, there's no space in the vector where the weight can be stored. So at some point, I have now here my edge weight map, or edge weight vector, or whatever you want to imagine what this thing is. And now I need to get all my edges first, so I call the edges function. The edges function returns a pair of iterators, which I used before just to iterate over all the wedges. What I do now, I take the iterator, I call another function called put, and I say, please put into that edge weight map for this edge the weight 2. This is the first edge, the top edge from the top left to the top right corner. And I want this edge to have a weight of 2. And I can do it by calling a function put. And I just need to pass in here a couple of parameters. And this way I can access the weights of each and every edge individually. All right, we have seen already that it can be a bit complicated if we want to define multiple properties, because we have to nest these things somehow. Or actually, no, I was talking about the visitors. Sorry, I have to go back one slide. If we want to define multiple properties here, we have to use the same trick as with the pair. This property class does not only accept here a tag and a type for that property, there can be also a third parameter passed, which has to be another property. So if you want to define multiple properties, you have to nest these properties again. That can get ugly. So there's another way to define properties. There's something called bundled properties. That is a bit more natural and a bit easier to use. In this case, I just define my own struct and say, all right, here in this struct, I define all the edge properties I need. And for my example, I need, as usual, a weight. All the edges should have a weight. So it's just a struct. And now I use this struct edge properties here as a template parameter. So I don't need to use this property thing anymore with the edge weight t thingy and whatever. I just use the struct as is. Now all the edges in my graph has a member variable weight, where the weight can be stored. That's nice. But I have another problem now. How does Dijkstra shortest path know that this is a variable where it will find the weight in? Before that, I used the edge weight t stuff. That was all built into BoostGraph. But now I have to tell that algorithm, listen, you have to use this variable because that's where you will find the weight. And you see how this works here. I'm using, again, the version of the algorithm with the named parameters. And you see, again, the code gets a bit ugly. I cannot pass multiple named parameters. This is the first named parameter, predecessor map. If I want to pass in a second named parameter, I have to call a function on the object which is returned by predecessor map. And that's how I can pass a second named parameter. And I have to call here weight map because I have to tell this algorithm somehow where it finds now the weights for the edges. And then I have to call here get again and have to tell somehow this weight map function, you will find the weights in the graph, in the struct edge properties, in the member variable weight. And then the algorithm understands where it has to look up the weights for the edges. How do I set the weights? The weights are still internal in the graph. It's still a property somewhere in my graph object. I still need to set the weights somehow. You see, even with this approach, I can just pass an array to the constructor. When I use these so-called bundled properties, it's called bundled properties because you can easily bundle a couple of properties. It's just a bunch of member variables. If you use these bundled properties, you can also, again, access these properties individually per edge. We have seen how this works before. We will have a look now at how it works with these bundled properties. It's a little bit easier, the code. So you call, again, edges to somehow get access to the edges. Edges is this function which we have seen in the first part of the talk. You get the two iterators, begin and end. I just want the begin now. I want the iterator for the first edge in my graph. Then I can use the graph a little bit like an array. So I can dereference the iterator. I will get then an edge descriptor. I can look into the graph and say, okay, give me the edge for this edge descriptor. And this edge has then, that is then really nice, all the member variables which I have defined here in my edge properties type. So I can access now a weight member variable of these edges, and I can just set the weights like this. Hui. Everyone is still awake? Okay. So that was a quick overview on how BoostGraph is used. I'm not going to talk about all these algorithms there are, because I think that's easy, and it really depends on what you want to do. I mean, some people want to find the shortest path, other people want to do something completely different. And I think the documentation here is actually good and helpful, so there is a good explanation what these algorithms do. What is really important to understand these concepts, which I was just trying to explain, there are these named and these unnamed versions. There are all these properties, and depending on at which examples you look like, it can be really confusing, because one example does this, the other one does that. But there is some logic, and I was trying to explain you what this logic looks like. So that was the idea of this talk. If you have any questions, please go ahead.
A very good source for the samples are not enough are the tests.
Okay. Okay.
Usually the tests can you show how to use an algorithm very good.
Yeah. So Jens is saying that the tests are a good source to find out how these algorithms are used. Yeah. Please.
During the actual limitation in the number of vertices, how does this scale up basically? And how does it work for the allocation of kids? If you want a 100,000, you want to scale up to Facebook.
Yeah.
Is there
The question is if you can use BoostGraph if you want to build up a company like Facebook. I have no idea. I have no idea.
indirectly, how does it scale up in terms of
Yes, the question is how it scales. I don't know. Yeah. So I should come up with another talk, not BoostGraph for dummies, but BoostGraph for experts. Oh, Timo.
Is that you can use your own data structures and plug it into the BoostGraph framework, and then it depends on your data structures how it handles that.
okay, fine, okay, good.
Jens?
There is also a parallelization for BoostGraph.
Yes. Yeah. Yeah, Jens says there's a parallel version of BoostGraph. I also read a little bit about it. When you click on this link and you look at the BoostGraph documentation, I think there's a reference to it, but I also never managed to even click on this link.
Has BoostGraph been updated since 2000, 2001?
Yeah, that's a good question. The question is whether BoostGraph has been updated since 2000, 2001. Yeah, I checked the book. It's really very old. And there's some things like Chandler asked, why do we need to nest all these pairs somehow? Why can't it be just a tuple? I looked a little bit at the header files, and it's a pity that Andrew isn't here. He has just given the talk on the concept light thing. Maybe he also needs to relax, because I've seen his name in many, many header files. So maybe he could have told us a little bit more. And I've seen also copyright notes in the header files from 2009. So it looks like that people have been adding algorithms in the previous years, but there are definitely certain parts of the library, and especially also of the documentation, where you would hope that somebody is going to update it. Yeah. Any other question? All right, we are then done, and we still have some time for pizza and Coke. Thank you very much.